Section: Introduction. In this section, we discuss the concept of automated machine learning, AutoML, and its significance in simplifying the process of converting raw data into accurate predictions. AutoML frameworks aim to make machine learning more accessible by incorporating best practices in data preprocessing, model selection, training, and deployment. This democratization of machine learning empowers both technical and non-technical users to create high-performing models efficiently without in-depth knowledge of machine learning techniques. The advancements in machine learning, especially the introduction of foundation models pre-trained on large datasets, have transformed fields like computer vision and natural language processing. However, there is a lack of dedicated open-source AutoML tools for fine-tuning these models for specific domains. Existing AutoML frameworks mainly focus on basic tasks like classification and regression with tabular data, overlooking the complexities of real-world problems that involve multiple data types. To address these challenges, we introduce AutoGluon-Multimodal, AutoMM, an open-source AutoML framework designed for multimodal learning with foundation models. AutoMM, integrated into the AutoGluon ecosystem, allows users to fine-tune foundation models effortlessly with just a few lines of code. It supports various data modalities such as text, image, and tabular data, enabling tasks like classification, regression, object detection, semantic matching, and image segmentation. The evaluation of AutoMM faces challenges due to the lack of benchmark datasets covering multiple modalities and tasks, as well as the scarcity of competing AutoML libraries with similar functionalities. To overcome these challenges, we curated a benchmark dataset comprising 55 publicly available datasets covering diverse tasks. In comparison with AutoKeras, AutoMM showed superior performance in basic classification and regression tasks across different datasets. For advanced tasks like semantic matching and segmentation, AutoMM demonstrated comparable performance with task-specific open-source libraries. AutoML has become a crucial area of research aiming to automate complex machine learning processes. Traditional AutoML methods focus on basic tasks like classification and regression, primarily for tabular data. While some frameworks can handle multimodal data, they often rely on traditional machine learning algorithms. AutoMM, on the other hand, is specifically designed to manage multimodal inputs efficiently, including image, text, and tabular data, in a unified framework with minimal coding requirements. Section Summary. In this section, we introduce AutoGluon-Multimodal, AutoMM, an open-source AutoML framework tailored for multimodal learning with foundation models. AutoMM allows users to fine-tune foundation models effortlessly on domain-specific data with just 3 lines of code, supporting a wide range of modalities like text, image, and tabular data for tasks such as classification, regression, object detection, and image segmentation. Through evaluations, AutoMM outperformed AutoKeras significantly in basic tasks and showed comparable performance in advanced tasks like semantic matching and segmentation, highlighting its potential as a comprehensive solution for automated solutions across various modalities and tasks. Section: AutoMM. In this section, we will discuss the challenges we face in supporting various data types and task varieties while adhering to the AutoML principles. The main difficulty lies in automating these processes using a unified approach for data format, processing, APIs, model design, and training workflow. We will now explain the design and features of AutoMM. When it comes to data format and processing, AutoMM utilizes Pandas dataframe to combine different data types like images, text, and tabular data, numeric and categorical. Data frames are widely used in data analysis due to their flexibility and ease of use. Essentially, a Pandas dataframe organizes data into a 2D table, where rows represent individual samples and columns represent features. Each field in the data frame can hold various data types such as numeric values, categories, text, image paths, byte array images, or base64 encoded images. This flexibility allows users to input multimodal data frames with any mix of data types. Additionally, Each data type can have multiple columns, enabling complex data representations. AutoMM, as an AutoML tool, effectively manages raw and noisy data, reducing the preprocessing workload for users. Traditionally, dealing with different data types involves creating separate data processing pipelines for each type, leading to redundant code and increased maintenance. To address this, we analyzed these pipelines systematically and identified commonalities to create a generalized pipeline. Our unified data pipeline includes components like Lightning Data Module, Torch Data Loader, Torch Dataset, a modality detector, a data preprocessor, and various data processors. At a high level, the Lightning Data Module uses Torch Data Loader to generate data loaders for training, validation, and prediction. The Torch Data Loader requires a Torch dataset, which depends on the data preprocessor and data processors. These components are determined based on the detected data types by the modality detector. The relationship among these data modules is illustrated in a figure. The data preprocessor handles general data processing tasks like filtering features, data type conversion, handling missing values, and normalizing numeric data. On the other hand, data processors manage model-specific processing requirements. Since multiple models may work simultaneously, each accepting multiple data types, we create a specific data processor for each data type of every model. The data preprocessor conducts preprocessing at the dataframe level during Torch dataset initialization, while data processors perform real-time transformations of individual samples during data loading. Additionally, we define data collator functions to group processed samples into mini batches for model input. Data processors handle per-sample processing, including data augmentation and multi-field processing. For image processing, tasks include augmentation, tensor conversion, and normalization. In cases with multiple images per sample, AutoMM processes each image separately before combining them. Text data undergoes tokenization, where each text field is tokenized individually and then concatenated into a single token sequence. To handle model-imposed sequence length limits, we truncate the sequence by iteratively removing tokens from the longest text field until compliance is met. In terms of APIs, AutoMM simplifies the fine-tuning of base models on single or multiple data types through a concise interface. For instance, for basic classification, regression tasks using a data frame stored in train.csv with a label column, label, users can import the multimodal predictor, initialize an object, and start training with just 3 lines of code. During training, AutoMM automatically identifies the problem type, splits the data, detects data types, selects suitable base models, and fine-tunes them. The fit method also allows customization options such as adjusting training time, hyperparameters, or conducting hyperparameter optimization. Continuous training is supported, enabling incremental training on new data. After training, users can utilize various APIs for evaluation or inference, including model evaluation, prediction, probability estimation, for classification tasks, and feature embedding extraction. Prediction-related APIs do not require labels, enhancing their deployment utility. Models can be saved and loaded for future use, with support for training resumption in case of interruptions. Additional resources like installation instructions, tutorials, and a cheat sheet summarizing key features are available on the official website. Section Summary. In this section, we introduce AutoMM, an AutoML tool that addresses challenges in supporting diverse data modalities while adhering to the AutoML philosophy. AutoMM utilizes Pandas dataframe to consolidate various data types like images, text, and tabular data, streamlining the handling of raw and noisy data through a unified data pipeline. With a concise API interface, AutoMM simplifies fine-tuning foundation models on unimodal or multimodal data, automating tasks such as problem-type inference, data partitioning, model selection, and customization options for training and evaluation. Section: Models. In this section, we aim to apply foundation models in various real-world scenarios. These models are first pre-trained on large datasets and then fine-tuned on smaller labeled datasets. However, This fine-tuning requires alignment between the data types used during pre-training and those in the specific task. For example, while BERT can be fine-tuned for text tasks, it cannot directly handle tasks involving both text and tabular data. Most foundation models are pre-trained on image-only, text-only, or image-text data, but real-world applications often involve more complex combinations like image-text-tabular. To address this, our AutoMM approach uses a late fusion architecture that can handle different combinations of data types. The late fusion framework integrates separate backbones for images, text, and tabular data, followed by a fusion module, such as MLP or transformer layers, for combining features. When only one data type is involved, the fusion module is not used. Importantly, adding a new data type can easily be integrated with existing ones. AutoMM is compatible with various model repositories like Hugging Face, Transformers, TIM, and MM Detection, which offer a wide range of pre-trained models. These models vary in size and performance, and AutoMM provides preset levels to balance performance and latency. For training, AutoMM typically trains a single late fusion model with fixed hyperparameters determined through offline searches on benchmark datasets. Unlike some other AutoML tools, we focus on offline tuning rather than further optimization or model ensembling. This approach saves time and resources, especially considering the resource-intensive nature of fine-tuning foundation models on multimodal data. We leverage the Lightning framework to streamline the training process, making it more efficient and scalable. To address challenges posed by large model sizes and limited computational resources, AutoMM incorporates parameter-efficient fine-tuning techniques like BitFit and LoRa. These techniques optimize only a small portion of pre-trained weights or introduce lightweight structures to reduce memory usage and training time while maintaining performance. Additionally, AutoMM supports distributed training and low-precision training to further alleviate the computational burden of training large models. Section Summary. In this section, we introduce the AutoMM framework that leverages foundation models pre-trained on extensive datasets and fine-tuned on smaller downstream labeled datasets, requiring alignment between data modalities. To address the limitation of existing foundation models that do not support multiple modalities like image plus text plus tabular, AutoMM adopts a late fusion architecture scalable to accommodate various modality combinations. By utilizing a preset model selection process and parameter-efficient fine-tuning techniques, AutoMM aims to streamline training workflows and optimize model performance, even for users with limited computational resources. Section: Deployment. In this section, we focus on deploying trained models efficiently into real-world applications. We make sure that predictor loading is smooth in offline environments by pre-saving necessary artifacts, like Hugging Face model configuration, to prevent internet access errors when the predictor is called. In production settings, having low inference latency is crucial, especially for online inference. While our training relies on Lightning modules that are good at handling large sample sizes, they can slow down inference when dealing with few samples. To tackle this issue, we offer a real-time option that skips Lightning modules in favor of plain PyTorch models and data processing to speed up inference. Additionally, we integrate with NVIDIA Tensor RT, known for its low latency and high throughput in deep learning inference optimization. Moreover, we handle different image formats between training and deployment, such as image paths in training and image byte arrays in deployment, by dynamically inferring image subtypes during inference to ensure smooth model deployment. We also extend traditional AutoML to cover advanced tasks beyond basic classification and regression. Currently, our system supports tasks like semantic matching, object detection, and semantic segmentation. Semantic matching involves evaluating the similarity between two items, which could be two images, two texts, or an image-text pair. We use a bi-encoder design to encode the two items separately in the embedding space before calculating their semantic similarity. Object detection and semantic segmentation are computer vision tasks where object detection finds object instances in an image, and semantic segmentation categorizes each pixel in an image into a class or object. Object detection provides object class labels and bounding boxes, while segmentation generates segmentation masks. Even though these tasks are complex, users can implement solutions with just 3 lines of code, but they need to specify the problem type when initializing the predictor object. We achieve these advanced functionalities by fine-tuning foundation models from Hugging Face and MM detection, like using CLIP for image text matching, Dino for object detection, and the Segment Anything model for semantic segmentation. In our experiments, we aim to evaluate the effectiveness of our system compared to other top AutoML solutions or task-specific toolboxes across various tasks like classification, regression, semantic matching, object detection, and semantic segmentation. Section Summary. In this section, we focus on the deployment of trained models, emphasizing the importance of efficient deployment for real-world applications. We address challenges such as low inference latency by offering a real-time option that prioritizes speed, integrating with NVIDIA TensorRT for optimized deep learning inference. Additionally, we expand AutoML capabilities to include advanced tasks like semantic matching, object detection, and semantic segmentation, showcasing competitive performance and user-friendliness compared to specialized toolboxes like Sentence Transformer. Section: Object Detection. In this section, we selected various downstream tasks from different domains and compared our AutoML model, AutoMM, with baseline frameworks from Vertex AI and NVIDIA DAO. Our comparisons showed that AutoMM outperformed other AutoML object detection solutions in terms of both performance and speed, all while being easier to use. While Vertex AI offers efficient tools for model development and deployment, it may have limitations in terms of pricing flexibility and customization options compared to other solutions. Due to the high cost of Vertex AI, we focused our experiments on evaluating it using the higher accuracy, new option on only 4 datasets. On the other hand, we conducted a detailed comparison with NVIDIA DAO using a pre-trained FAN-L hybrid backbone. It's important to note that both Vertex AI and NVIDIA DAO have specific data requirements, requiring additional preprocessing beyond the common COCO format. In contrast, AutoMM can be easily used with just a few lines of code without the need for extra data processing or configuration. For more detailed information on the datasets, baseline methods, metrics, and setup details, please refer to the appendix. Moving on to semantic segmentation, this task involves dividing an image into semantically meaningful regions and assigning a class label to each pixel, providing detailed information about the spatial extent of objects in an image. Our AutoML semantic segmentation solution was compared with SAM Adapter and Detectron 2, even though the latter two are not AutoML solutions. Our evaluation showed that our AutoML solution outperformed SAM Adapter and Detectron 2 across multiple metrics, demonstrating its effectiveness and competitiveness. Furthermore, our AutoML approach simplifies and enhances the process of semantic segmentation for various real-world applications. When comparing AutoMM with other open-source semantic segmentation toolboxes across datasets from different domains, AutoMM showed superior or comparable performance with minimal trainable model parameters. This was achieved through parameter-efficient fine-tuning, providing effective segmentation results within a low-parameter budget. Additionally, AutoMM offers a more streamlined training setup compared to other toolboxes, eliminating the need to rewrite data loaders or configuration files for new datasets. For more detailed information on datasets, baseline methods, metrics, and setup details, please refer to the appendix.